What's this Saturday's date coming? March 14th, one of my favorite days of the year. It's Pi Day, but it's a Saturday, so we're going to do all stuff this week. All of you who have already completed Calc 1 should be doing this on Wednesday. There are prizes. You should participate in the integration. It's like a spelling bee, but with calculus. It's a lot more fun than a spelling bee, in my opinion. But that's me. Register. Go. Wednesday night. We'll have fun. Friday, you know what a haiku is? Syllable counts. We're going to do haikus. 3 syllable, 1 syllable, 4 syllables. Pi Day, right? Recite the largest number of digits of pi, win a pie. Last year's winner did 150 from memory. I don't expect you to top that. I just want to know who gets the big one this year. There will be trivia on and off all day long. So come celebrate Pi Day with us in the Math Center this week. Y'all should be registering for this, for the integration bee, because I know if you finished Calc 1, you know how to do integrals. Meanwhile, I'm going to blow your minds. If I asked you how many tables there are in this room, how would you find out? Count them. How do you count them? Come on. So 1, 2, 3. Okay, but here's an interesting part. You went across. Does it matter if I go across? What if I go back and forth? What if I go up and down? It doesn't matter? Why?
No, to get them all.
Okay. So really, if I define the number of distinct elements in a set, we had a symbol for that. We called it the cardinality of S. We said this was the number n, so that there were n items, as long as that number is finite. So in the answer to my question is there are 18 desks in this room. And it doesn't matter what order I count them in or how I count them, as long as I get all of them. This is desk 1, 2, 3, all the way up to 18. No matter how I do that, I will come up with 18 at the end, right? So another thing I can think of, and another way to define this cardinality, is to say I have a function from the set A not S, not B, S. And the set A is the numbers 1 through n, and it goes to S, the set of things I want to know the cardinality of. Now, this counting idea means that I'm going to be able to say, that's desk 1, that's desk 2, that's desk 3, that's desk 4, that's desk 5, right? I'll be able to pick a set element for each number. Wait a minute. Hang on a second here. I can't say this is desk 1, this is desk 2, this is desk 3, that's not going to work, is it? So not only do I have to get all of them, what's a function that gets all of them called? That's the homework I just gave back. So chapter 2, section 3, you turned it in on Friday. That's what we were doing on Friday. That's not the assignment we turned on Friday, but a sequence is an example of a similar type of function. I want to make sure I get all of the things in S. A function that hits everything in the codomain, right? Domain, codomain. A function that hits everything in the codomain. What did we call such a function? There was an adjective for it. A function that's onto, right? So it's got to hit everything. And I can't hit anything twice. What do we call a function that hits everything exactly once? One-to-one. A function that does both of those is called a bijection. If I have such a function, then this number n is the size of set S. Now, here's the best part. I don't care what function you use, as long as that function is one-to-one and onto, which is why, like I asked, doesn't matter what order we count in. If I count from left to right, back and forth, I'm going to be really technical about this. If I go back and forth in rows like that, that's called bostrofeeding, as the ox plows. I love these weird words you would find. Formal Greek writing was written left to right on one line, and then right to left, and then left to right, and then right to left. It was written in that fashion. How weird. Anyhow, if I go back and forth, that's fine. If I go up and down the columns, that's fine. If I go 1, 2, 3, in any order, it doesn't matter, as long as this function is one-to-one and onto. I'm going to define this in general. Let's actually say this for any two sets. If there exists a function f from A to B that is a bijection, then cardinality of A will be equal to the cardinality of B. So two sets are the same size. If I can write a one-to-one and onto function from one set to the other. By the way, if I have a function from A to B and it's one-to-one and onto, I have an inverse from B to A, right? Just turn all the arrows around. I have the set from 1 to 18. I have the tables in here. I could put 18 numbers on a card, and as long as there's one card on every table, doesn't matter how I lay them. There's nothing in here about the size of A or the size of B. Let's consider for a moment this set. What is this set again? Natural numbers. I'm going to go ahead this time and include 0. So this is the set. 0, 1, 2, 3, 4, and so on. This set is not finite. There is no number n where you can do this. If you picked any number, 735. and you said that this size is set 700, the size of this set is 735, then I'm just going to start counting. 0, 1, 2, 3, 4, dot, 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 736. Oops. I got too big, right? This set is not finite. But it is still counted, right? I can think of the first number, the second number, the third number, the fourth number. Since I included 0, it would be the first, the second, the third, the fourth. But it doesn't really matter, does it? Even if I left off 0, it still wouldn't be finite. In either case, when I have a finite set or a set that is the same size as the natural numbers, then A is a countable set. If A is not finite, we call it countably infinite. So the natural numbers themselves are a countably infinite set, but they are still countable. Make sense? I can think of laying down cards and just never stopping. We're going to give a symbol to this size of infinite set. The size of the natural numbers is called Aleph null, or Aleph 0. The Aleph is the first letter in the Hebrew alphabet. It is technically a silent letter. So I can now think about countable sets. A set that is finite or a set that is countably infinite just goes on forever, right? So we look at this set. And I want to compare this to other sets that I know to be infinite. Consider this set, the integers. How many things are in this set? Infinite. But there's a question there. Is this set countable? It's not finite, but it could be countable. Remember, I'm going to scroll back up here. Two sets of the same size if there's a bijection from one to the other. But when I think about the integers, I think about all of the natural numbers, right? 0, 1, 2, but all of the negative ones as well. So you might think that since Z looks like this, it's got more stuff in it than the natural numbers, doesn't it? There are more integers than there are natural numbers. No. I'm about to hurt all of your brains. I claim this set is the same size as the natural numbers. And Grace, I'm very happy to see your face wearing the same expression my face wore the first time I saw this. You gotta be kidding me. There are more things there. No, there aren't. I'm going to write you a bijection. The only way I know those are the same size is if I can build this bijection, right? So I need a bijection. So here's what I need you to do. I need you to put a natural number on each integer in a one-to-one and on-to fashion. I'm going to start with the easy one. I'm going to start with 0. That integer is first in line. Positive or negative? Flip coin. Positive or negative? Positive. Then the next number is 1. The number after that is -1. The number after that is 2. The number after that is -2. The number after that is 3. The number after that is -3. Here's a question for you. Are you ever going to hit the same integer in the bottom row more than once? If you think about this line, you start in the middle. You said positive, so I went right first, then left, then right, then left, then right, then left, then right. Am I ever going to hit something twice? It's 1-to-1, and it's onto. I'm never going to miss an integer, am I? This is a bijection. It's 1-to-1 and onto. And that means these two sets are the same size. Whoa. That's really weird. The natural numbers are a subset of the integers. A proper subset of the integers. There's at least one integer that's not a natural number, but that set is still the same size. Infinity is weird, man. Maybe you don't like this example. Here's another set for you. I'm going to let E be the non-negative even integers. So that's the set 0, 2, 4, 6, 8, and so on. Is this set finite? No. Clearly not finite. Is it countable? Again, I'm going to make the claim that the size of E is Aleph null. It's the same size. All right, wait a minute. I take the natural numbers and I throw out half of them. Take away 1 and 3 and 5 and 7 and 9 and throw them all out. And I don't have any fewer things. I'm going to write this function as a formula. F from the natural numbers to E is given by f of x is 2x. So f of 0 is 0. F of 1 is 2. F of 2 is 4. F of 3 is 6, right? It's 1 to 1. Because if you have two numbers and the outputs are the same, you divide by 2, the inputs must have been the same. It's on 2. The output of this is always an even number. And if you start with something that's non-negative, this can never be negative. So you're going to get all the non-negative even integers. This is 1 to 1, and it's on 2. They're the same size. Now here's something even weirder. The even numbers are clearly smaller than the natural numbers. And that means they're even smaller still than the integers. Yet all three of those sets are countably infinite. They're exactly the same size. Mother... I have a couple of illustrations that kind of make this weirder or clearer, depending on what you like about this. At the beginning of the 20th century, 1902 Mathematics Association conference, a mathematician by the name of David Hilbert created a list of problems in which he claimed that understanding and working out the math behind these problems would drive mathematical innovation and the future of knowledge for the next 100 years. There are entire books dedicated to single problems in David Hilbert's list. There's one in the library on the 10th problem. The same idea happened at the beginning of the 21st century when the Clay Math Institute created 7 problems and said, not only do we think these are the problems that will drive the next set of mathematical innovation, we're going to offer $1 million prize for each one. So far, one of them has been solved. And the guy turned down the money. We'll talk about another one in a couple of days, but Hilbert actually came up with the idea of the countable hotel. I want you to imagine a hotel building. Where each door has a natural number on it. Each room, there's room 0, 1, 2, 3, 4, and so on forever. There are Aleph null rooms. They're all full. Here's a question. All the rooms are full. You show up to the hotel. Can we find you a room? You don't already have one. Can I put you in a room?
Yes, because they're infinite rooms.
Okay, so how do I put you in a room? I can't send you to the last one. There isn't one. Where do I put you? The manager says, absolutely, I've got a room for you. What's your room number? Here's a hint. It's on the screen. 0. I'm going to put you in room 0. Because I'm going to take the person in room 0 and put them in room 1. Take the person in room 1 and put them in room 2. If I take each person and move them down a room, doesn't that leave room 0 open? Does anybody not get a room? This is 1-to-1. It's not onto because it misses 0, right? But it is 1-to-1. So everybody still has a room, and you have a room now too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 of us in the room. We all show up. Do we each get a room? How? Instead of adding 1, I had 12. An entire school bus pulls up. Well, how many people are on the school bus? Just move down that many rooms. It works. It's weird, but it works. Here's a set that's even bigger than the set of integers. Clearly, wait a minute, what are rational numbers again?
Any number that can be a fraction.
Any number that can be written as a fraction with an integer on the top and an integer on the bottom. Now I'm only looking at the positive ones. There are more of these than there are integers, right? Because all the whole numbers, 1, 2, 3, 4, 5, you just put them over 1. But I got all the halves and the thirds and the quarters and the 13ths and the 77ths and so on, right? There's got to be more of these. What do you mean no? What do you mean no? I want to write out a list of all of the fractions in order. What order? I'll write them by denominator. This is going to be a lot of writing, isn't it? I've got each row has a top that keeps going on forever, and each column has a denominator that keeps going on forever. Now I want to line these up. Do I go down or right first? I'm going to start here. That's the first number in the list. Now for the second one, you can either go down or right. Take your pick. Now go diagonally. That's a new number. I've never hit this one before. So that's the third number. Now we go over. That's the fourth number. Now we go back in the diagonal, but I've already hit this because 2 over 2 is the same as 1 over 1, isn't it? I want my function to be 1 to 1, so we're going to skip that. Then I go down here. I've not hit 1/4 yet. I've not hit 2/3 yet. I've not hit 3/2 yet. I've not hit 4. I've not hit 5. Oh, wait, I already hit 4 over 2 because I did 2 over 1. So I get to skip this. 3 over 3, I get to skip that. 2 over 4, I get to skip that. This one will be 1 over 5, so I'll go all the way over here. Am I eventually going to hit all of them? Am I going to hit any of them more than once? I keep skipping it every time I've run into something I've already done. This is a 1-to-1 and onto list. I can't tell you what the 75th number in this list is, not without actually building the whole thing out, but it's definitely a 1-to-1 and onto function. And that means this set of numbers is the same damn size. I'm starting to get angry here. Because so far, every time you give me a new set, I come up with no, it's still not any bigger. By the way, there is a picture of this on page 187. This same idea. All right. I've got another set. One more set. All of the numbers between 0 and 1, real numbers, not rational, not countably fractions, but all of them, real numbers. Okay. This was an argument put forth a guy by the name of George Cantor. And George Cantor, in the late 1800s, was trying to work on the theory of infinite sets, trying to understand what was going on here. And George said, I think this one's not countable. Now, it's going to be very difficult to show something is not countable, because what you have to do is you have to rule out any possible bijection. You have to show that there is no way to make a function that is 1-to-1 and onto here from this set to the natural numbers. That means it's going to be very hard to do this directly. This is a bad direct proof. Probably a bad indirect proof. But it turns out to be a wonderful proof by contradiction. How does a proof by contradiction work again?
That one like number that isn't true.
That's finding a counterexample. If I just find one number where it isn't true, that finds me a counterexample. A proof by contradiction is supposed to lead me to something that contradicts an earlier assumption, right? So I'm going to assume what I want is false and then find that contradiction.
So assume it's countably.
Right. So we start by suppose this is countably infinite. Now, the definition of being countably infinite is there's some bijection. So, there exists f from the natural numbers 2, 0, 1, a bijection. That means that for every n in the natural numbers, f of n is some real number. Matter of fact, I'm going to use r, not x. Rn. A real number between 0 and 1. That means there's a first, a second, a third, a fourth, right? So, my list looks like this. F of 1 is R1, F of 2 is R2, F of 3 is R3, and so on. Yes? I left off the 0 this time, so I started my natural numbers at 1 instead of at 0. You with me so far? What do I know about this number R? I know it's between 0 and 1, right? So that means that this number is 0-point stuff. Because it's got to be smaller than 1, it's got to be bigger than 0. And in order to prevent that 0.999999 bullshit, we're going to say no number can end in an infinite tail of nines. So let me think about this. R1 is 0 point digit 1, digit 2, digit 3, digit 4, and so on. Since these are all part of the first number, I'm going to make it 1, 1, and 1, 2, and 1, 3, and 1, 4. That's not 11, 12, 13, 14. Those are two separate indices. We can even put a comma between them if you want to remind ourselves that that's the first number's first digit, first number's second digit, and so on. Yes? What's R2 look like? Ah, 0 point D21, D22, D23, D24. R3 is just going to change those to be 3s. Same with R4, 4-1, 4-2, 4-3, 4-4. And we keep going, right? There are infinitely many of these numbers. So Ri is 0 point Di1, DI2, DI3, DI4. Way out here somewhere is DII, and it keeps going. Now, maybe, like if I did 0.5, all of those after the 5 would be zeros, wouldn't they? 0.5, 0, 0, 0, 0, 0, and so on. But it could be 0.123, 123, 123, 123, couldn't it? It could be 0.123, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Could be any list of numbers I want. I know it'll be pi minus 3, 0.141592653. Like I said, I don't remember enough digits to win the prize. This is a bijection. It's 1 to 1, and it's on 2. Cantor said, no, I'm going to write a number that you missed. I don't know what order you put the numbers in, but you still missed one. Here's my new number. Dean, give me a number. And between 0 and 9, pick a digit. 6. The new number I am going to create is made up of only 6s and 0s, because you picked 6. But what we do is we build this number one digit at a time by looking up here. In this row, I am going to look, sorry, those should not be R's. These should be D's. In the first thing I'm going to look at is I'm going to look at this number right here. If that's anything other than a 6, then R star's first digit is a 6. If that happens to be a 6, then I'm going to make it a 0. Then I go to the second digit and I look at this. If that's anything other than 6, I'm going to write down a 6 for the second digit of my number. If that is a 6, I'm going to write down a 0. Third digit, fourth digit, ith digit. Right? Now here's what Cantor said. Cantor said R star is not in my list. How did he know? Why can I agree with him? R star is not on my list. Can't be on my list. If it was on my list, it'd have to be somewhere on the list, right?
Is it because like they're all decimals, 6 is in the decimal?
6 is a decimal. 6 is a number between 0 and 9. It's either
Between 0.
oh no, because it's 0 point, right? I did it again. This is a D, right? The digit. So let's say this one was 0.1, then this number would start 0.6. If this starts 0.13, then this is 0.66, right? I just have to build this one from knowing what these numbers are. Why can I say now that R star cannot be anywhere on my list? Could R star be the first number in the list? Could R star be that number? But we described this number by making sure its first digit did not match this, right? The first digit of R star is different than the first digit of R1. So R star is not R1. Can R star be R2? The second digit of R star is different than the second digit of R2. Can R star be R3? Could it be R4? Could it be Ri? No, because it's different here. Can it be any number on our list? No, the way we built it, it's different by at least one digit for every number in our list. Which means our list has a problem. Our list was supposed to be onto, right? It was a bijection. It was 1-to-1 and onto. You missed something. Now, here's the best part. I didn't ask you how you built the list, did I? No matter what way you built the list, no matter how you counted, you'll miss one every time. There's at least one number more than this list. And that means that the function f fails to be onto. F missed a number. F is not onto. There's my contradiction right there, because we started this discussion with F as a bijection. There's my contradiction. This argument is called Cantor's diagonal argument because he made that diagonal construction, right? This pissed off a lot of people because what Cantor said is I need to be able to choose this number by making infinitely many selections along the diagonal at once. Now here's a computers versus theory argument. If I want to write down the digits one at a time, I'll never finish, will I? But I can claim there's a number that's different without ever writing it down. Constructive versus non-constructive proof. This non-constructive infinite idea of choices pissed off so many people that there was like a 65-year argument over whether this idea of choosing infinitely many things at once is allowed. The argument is still going on in set theory today. It's called the axiom of choice. And by making it an axiom, you can allow people to make infinite many choices at once. Or you can refuse to allow this axiom. These are called constructible numbers versus declarable numbers. If I have to build it one digit at a time, I can't do infinitely many choices at once. But if I can declare the number to exist, then I'm using the axiom of choice. People who work in set theory decide which set theory axioms they want to use. And if you want to use the axiom of choice, you can. If you don't want to, you can. The math you get is different. And a lot of finite state behavior in computer science is based off of the idea of constructibility rather than declarability. By the way, the cardinality of the set from 0 to 1 is not Aleph null. Because we just showed there's no bijection. So we're going to call this size C. It's a very angular looking, funny looking fractal, fractured sort of C for the continuum. It turns out this is a bigger infinity because we missed a number, didn't we? We missed something. No matter how we did it, we missed numbers that were in there. There are more numbers between 0 and 1 than there are integers. Because the integers are countable. And this continuum is bigger. There are different sizes of infinity. There are a lot of nice and very interesting results and very counterintuitive results that come from the idea of countable versus uncountable sets. There is a result in the textbook called the Schroeder-Bernstein theorem that shows that you can actually build one set into another, from set A to set B and set B to set A, with 1 to 1, but not onto, and still show that they're the same size. In any case, you should read that one. It's an interesting argument. I will see you all on Wednesday. Sign up for the integration bee, all you people who already finished calculus. I want to see y'all do integrals. Some of you were not in my calc class. I want to know you can do integrals. Come on, let's go kick butt. I'll see you all on Wednesday.